Thank you very much. Okay, so I'm going to talk about some joint work that I did with Rutger Campbell last year. So Rutger is a former PhD student of mine and he's now working at IBS in Korea. The work we did is on connectivity systems, and this all stems from this feeling you get when you work on matroid problems that connectivity, however painful it is a lot easier than some other things. So very often when you're trying to do, say, an excluded minor characterization, so for example, if you're trying to prove Kuratowski's theorem or something, you might be trying to keep certain properties in your graph, and you're trying to keep 3 connectivity, because 3 connected planar graphs have unique embeddings, and typically that's an important property. So you very often want to keep a certain connectivity property, then you want to keep something else. And you usually find that the something else is really difficult to work with, and connectivity is, at the end of the day, not so bad, although extremely painful. And so what we basically, we extend connectivity from matroids to these loose things called connectivity systems. There are even looser things out there that are related to connectivity that Diestel describes. This is not quite as abstract as that, but still fairly abstract. And hopefully they will behave nicely. That's the hope. So let me start out by telling you the statement of the theorem we prove, although I haven't defined anything, and most of you won't know the definitions of any of these words yet, but we define a containment operation on something called connectivity systems, and we show that in the class of unitary connectivity systems with bounded pathwidth, it's a well-quasi-order. And I don't expect you to even know half of those words now. The talk will explain that. But there's this theorem that I hope by the end of the talk you'll say, oh, it's a nice theorem. And we've derived from that theorem an excluded minor theorem about matroids. Now, just as a word of warning, I'm going to pretend that you're all experts on matroids in this talk. I have to define connectivity systems, and if I also defined matroids, there would be a serious choking hazard. So I'll pretend you're all experts on matroids, but it's not important if you're not, because you can just nod for the small parts that I'm really talking about matroids. But we're going to derive from this theorem on connectivity systems, a theorem on matroids. And one of the things I find interesting are the mechanics that go into how to take a theorem on connectivity systems and derive a theorem about matroids. So this is a theorem about domination, which is some containment operation in this abstract world of connectivity systems, and we derive excluded minor theorems in the worlds of matroids. And there's other notions of connectivity that I'll talk about, and you can also derive results in those settings with similar machinery. So I find this implication here an interesting thing, and I'll focus a lot on that in the talk.
So the way you've written that main theorem is not new?
The main theorem is new, and this is a new application of the main theorem. The other applications that you get in the other settings aren't new. I mean, you can apply this in various connectivity settings, and we'll see 4 different connectivity systems, and if you apply it to 3 of them, they're not new because the other well-quasi-ordering results are already known in those settings. Okay. This theorem is a theorem that I tried really hard for 20 years to prove something like this. So 20 years ago, a coding theorist asked me essentially this question, except in the world of binary matroids. Here, we already knew this was true because it followed from well-quasi-ordering results in binary matroids. But he asked, could I get a precise bound? And I was sort of annoyed that I couldn't. And I spent a long time over the last 20 years trying to get a precise bound, like just any bound. And I don't know how to get a bound on the size of these things, but you can get that there's finitely many from well-quasi-ordering type ideas. Okay, so Mostly what I want to do in this talk is just to convince you that it's an interesting topic. So I'll give you a gentle introduction to connectivity systems. I'll probably be quite vague at times, but basically explain a few different notions of connectivity and how they fit into the world of connectivity systems. And then we're interested in two width parameters, pathwidth and branchwidth. They're very easy to define. We'll see those. And then I'll tell you about how to take results on connectivity systems and then turn them into things you care about more in the applications. And then finally, I'll tell you a bit about well-quasi-ordering and this new containment operation. I won't really get into proofs of, well, not even really, I won't get into proofs of anything today. So I'm going to start out by motivating connectivity systems by talking about edge connectivity and graphs. So if I have a graph, I'm going to look at the vertex set of the graph, and for each subset of the vertices, I'm going to write down its connectivity. And its connectivity is going to be the number of edges connecting that set of vertices to its complement. Right, so this is basically just abstracting all of the edge connectivity information you could ever want from the graph into this function. So from the way we define this function, so I've got this function defined on subsets of V. It's symmetric because every edge that connects X to its complement connects its complement to X, so it's a symmetric function. And you've probably all seen that it's submodular in some place or other. So like you've come across the fact that this function is a submodular function. The connectivity of a set X plus the connectivity of some set Y is at least the connectivity of their intersection plus the connectivity of their union. You have presumably all come across that inequality dealing with edge connectivity at some point. So it's these two properties here that define connectivity systems in general. More specifically, what do I mean by a connectivity system? You have some finite ground set V, and then on every subset of V, you assign some non-negative integer connectivity value. And that connectivity function has to satisfy those two conditions. It has to be symmetric, so the connectivity of a set is the same as the connectivity of its complement, and the function has to be submodular. Okay? So that's what I mean by a connectivity system, and it turns out that connectivity systems come up a lot in combinatorics. Typically, when you're thinking about connectivity, you don't really just, like if I'm thinking about edge connectivity, usually I'm imagining the connectivity, I think about the connectivity between two sets of vertices, not just for a given partition, right? I might have two disjoint sets of vertices, and I'll be asking for the minimum, for the connectivity between them, which in the case of edge connectivity would be the size of the smallest edge cut, separating X from Y. But you can do the same definition for connectivity systems. You can take two disjoint sets, and you can define the connectivity between those two sets to be the minimum connectivity of a set Z that contains X but is disjoint from Y. And so it's just like once you've got a connectivity system, you can define connectivity between pairs of disjoint sets. Okay, so the nice thing is that so not only can you get the connectivity between pairs from the connectivity of a set, but you can go back the other way around too. So these things each define the other. So there are different ways you might define a connectivity system depending on what you care about. Pretty much the same thing is that there's a million different ways to define a matroid. There's two ways to define a connectivity system. Can't tell you a third off the top of my head. Okay. So when you think about this connectivity between a pair of sets in the edge connectivity case, the first thing that springs to mind is Menger's theorem. So the definition that we gave was talking about the size of the smallest cut, edge cut separating x to y, but Menger's theorem tells you that's the same as the number of edge disjoint paths connecting x and y. And as soon as you write out this, you think, hey, I could probably do the same thing for vertex connectivity. Right? I could replace edge connectivity by edge disjoint paths by vertex disjoint paths, and I could define a new connectivity system that way. So if I take two disjoint sets of vertices in a graph, and I let kappa be the number of vertex disjoint paths from x to y, now I can define lambda from kappa, and again, yes, you get a connectivity system. In this case, what is the lambda? So you'd be basically partitioning the vertex set into two parts and asking for the maximum number of vertex disjoint paths from one side to the other, which is just asking for the largest matching in that bipartite graph. It's slightly a weird definition when you first see it, but it's a natural thing. If you want to define a connectivity function on the set of vertices, that's the natural thing to do. So this is again a connectivity system, but this connectivity system has the property that every vertex has connectivity either 0 or 1. So singletons have connectivity 0 or 1, whereas in the edge connectivity case, you can have really large connectivity. Right? Singletons, the connectivity of a singleton is the number of edges that is its degree, basically. Right? So here you end up with connectivity 0, 1, and that's what I mean by a unitary connectivity system. So the connectivity of singletons is 0 or 1. So here's yet another unitary connectivity system that you can get from a graph, and this is, I don't think it's got a good name, but Boucher defined it, so today it's called Boucher connectivity. He defined this in the 80s. So people who work on things like circle graphs and such will probably have seen connectivities of this kind come up. So you take the adjacency matrix of the graph, and now I'm going to do all my linear algebra over GF2. So the connectivity of a set X, a set of vertices X, is going to be the connectivity of this matrix here, which has its rows indexed by X and its columns indexed by V minus X. And when you take the rank of that submatrix over GF2, that becomes the connectivity of the set X. And it turns out this is a unitary connectivity system. And because this is the Tutte seminar, I should point out that the vertex connectivity system that I just gave you can also be defined in a very similar way. But instead of taking the adjacency matrix, you take the Tutte matrix, which is a matrix associated with matchings. It's a skew-symmetric matrix, which has the same support as the adjacency matrix, but you put a variable x in for an edge and minus x in for the other side, and the variables are different for every edge. And then it turns out that the rank of this matrix here will just be the size of the largest matching in the associated bipartite graph. So you can also define vertex connectivity using ranks of matrices, and if you take any symmetric matrix, you could also just, it didn't really matter that we had a graph around. If I take any symmetric matrix, I could write out a connectivity system for that symmetric matrix or skew-symmetric matrix. When you just need the ranks of these two things to be the same for the point of symmetry, keeping the symmetric property. Okay. Here's yet another unitary connectivity system from matroids, and we're all geniuses about matroids, so we all know this one well. This is Tutte's connectivity system. So Tutte defined this notion of connectivity in the 60s. In terms of representable matroids, so matroids given by a finite set of vectors, you can take a set X of vectors and you can look at the subspace spanned by X, and you take its complement, look at the subspace spanned by X, and this connectivity is roughly telling you the dimension of the intersection with a +1. That's what this Tutte's connectivity function is telling you. It's telling you the dimension of the intersection of these two spaces, which really tells you how, from a linear algebra point of view, how connected that collection of vectors is to that collection of vectors. Okay?
Why is that +1 then?
Because the dimension of, it's always one less than it should be.
That's only with graphs. You don't want the +1 there. Are you talking about graphs?
What's the dimension of a point?
1?
0.
0.
Geometers, they're impossible. Hopefully we don't have any geometers here. Okay. So when you're dealing with connectivity, you usually have some natural associated containment operation that you care about. And or more often, it's the other way around. You care about some containment operation, and then you get led to a certain kind of connectivity that's related to it. And so edge connectivity is the kind of connectivity that you end up thinking about if you're dealing with immersion minors. And immersion minors, you're allowed to take subgraphs, and then you're allowed to do this splitting off operation, which is you take two edges incident with a vertex and shortcut it. Delete the edges and just replace this thing. This is a natural notion where when you care about edge disjoint paths, splitting off is somehow a natural operation to do. And so once you start thinking about immersion minors, you pretty quickly end up thinking about edge connectivity. And when you think about minors in graphs, you pretty quickly end up thinking about vertex connectivity. And then there are these slightly strange notions of minors called vertex minors and pivot minors that Boucher defined in the 80s, but already appeared somewhat earlier because of they come up naturally in the world of circle graphs, for example. They appeared earlier, but even more recently they've started appearing because they have interesting connections in quantum computing when you're doing measurement-based quantum computing. So they're slightly strange operations, but they come up in a lot of different ways. And so there are these two notions of minors that you get that end up, that when you think about these notions of minors, pivot minors is just a restriction of vertex minors. This is a more general version. These are both related to Boucher's connectivity. And Tutte was basically led to think about matroid connectivity by thinking about minors. Okay, so once you've got this containment operation and this connectivity notion, you typically want a Menger type theorem. And in all of these settings, there is a connectivity, there is a Menger type theorem known. So we all know the edge and vertex Menger theorems. So for the edge disjoint paths and vertex disjoint paths, in the 60s, Tutte proved a version of Menger's theorem for matroids. And much more recently, maybe 2010 or so, maybe probably a bit earlier, 2006, I think Sangilom proved versions of Menger's theorem for vertex minors and pivot minors. Now, what is Menger's theorem when you think about it through the lens of connectivity systems and such? It's not going to look at all like what we think of Menger's theorem as. What it says is that if I take two disjoint sets X and Y in a connectivity system, it's saying that I can remove the elements outside X and Y without reducing the connectivity between X and Y. That doesn't sound like Menger's theorem, but let's think about the edge disjoint version of Menger's theorem. Right, so the edge disjoint Menger's theorem says that the number of edge disjoint paths from X to Y is the connectivity from X to Y. So I can take one of the edge disjoint paths and I can use the splitting off operation to turn it into an edge connecting x and y. So for every path connecting x to y, I can turn it into an edge connecting x to y, and then I can delete all the other stuff. So now I've removed all of the things outside x and y, and I've kept the connectivity between x and y, because I've turned all those paths into edges. So that's what, I mean, if you look at each of those theorems that I just mentioned, these theorems here, they all say that, I mean, if you state them the right way, they all say that you can remove all of these things outside x and y without reducing the connectivity between x and y. All right, so we've got natural containment operations for all of our favorite connectivity systems, but we don't have one yet for actual connectivity systems. So what's a good containment operation for connectivity systems? So I want to have an operation that lets me remove elements. So I'm going to basically restrict it down to some set Z. So I need to define the connectivity of a set X inside Z. And I need the property that the connectivity of X is the same as the connectivity of its complement within Z. So the natural thing to do is to make the connectivity of X in the restriction the connectivity between X and its complement within Z. You just say it's that. And if you're lucky, it's a connectivity system, and it is. That's good, we're lucky, right? So you can restrict to X. I can just take a subset of Z, and I look at the connectivity in the connectivity system between X and the complement of X, so Z minus X. I look at the connectivity there, and I define that to be the connectivity of X when I restrict it down to Z. So that is an operation that you can do. You can restrict down to some subset of a connectivity system and keep a connectivity system. And in fact, if you started out with a unitary connectivity system, you keep a unitary connectivity system. So that's also nice. And the nice thing when you do this is that Menger's theorem is free, because you just defined this restriction operation to maintain the connectivity between pairs. It just did. Like, you don't have to do anything. You didn't have two choices of way to remove it. You only had one way to remove an element, and you remove it in a way that doesn't reduce the connectivity between anything. That's really convenient when you're in the middle of a proof, that you can just throw elements away and keep connectivities. I mean, if you think about various proofs you've done and you've had to fight to keep connectivity between certain things, and now you get it for free, this is nice. Okay, so that's a brief introduction to connectivity systems. And now I want to talk about the two width parameters that we care about today, which are pathwidth and branchwidth. Pathwidth is really very easy to define. So what does it mean that a connectivity system has pathwidth at most k? It means that you can order the elements in your connectivity system so that however you partition them respecting that order, you get connectivity at most k. So in other words, the connectivity of E1 up to EI, for any I, connectivity of that set is at most k. But that's what it means to have pathwidth at most k. It's a sort of a natural idea. And branchwidth is slightly more complicated, so let me tell you what that is. So it basically says that I can recursively decompose my connectivity system so that while I'm decomposing it down to singletons, I keep seeing sets with connectivity at most k. So I start out with my ground set. I have to be able to partition it so that I get two non-empty sets each with connectivity at most k. This isn't an arbitrary partition. This has to be a partition that allows me to keep partitioning. I mean, I might be able to keep partitioning if I do this one, but there might be some other one that I'm not allowed to do. So I'm just saying there exists a sequence of partitionings that works. So I partition it up, and then I take one of these sets, maybe this had size at least 2, and so I partition it into 2 non-empty sets. Each of those have to have connectivity at most k. And then I take one of the leaves, and I partition B2 up into 2 sets, and each of these have to have connectivity at most k. And I keep doing this until the sets at the leaves are singletons. And then I end up with this cubic tree where the leaves are labeled by singletons, and the edges all correspond to small separations of the original set. Right, that's what it means for a set to have branch width at most k. And the reason why we're always partitioning into 2, you can't allow people to just go, like, branch off into more sets, because you could just immediately branch off into singletons, and then all of the edges will just have low order, like in a unitary connectivity system that all have weight 1. That's cheating. Right, so we have to, we impose structure by only allowing us to split a set into 2 sets at each step. There's a really nice theorem in Susan Jowett's thesis that tells you that obstructions to branch width W are small. So if I have some connectivity system that's containment minimal with branch width bigger than W, then that connectivity system has size less than 3 to the W plus 1. In other words, if you give me any connectivity system with a branch width bigger than W, it's going to contain a small connectivity system that still has branch width bigger than W. So that you get this small witness of branch width being at least W. Right, that's her theorem. And you can prove from that theorem that the excluded minors for the class of matroids with branch width at most k are small. So here small means that there's some computable bound on their size. And this is not obvious, this implication here, because Susan Jowett's theorem is talking about containment, and this is talking about minors. So what you need is this theorem of Chen and Whittle. So let's just forget precisely what the theorem says, and let's just think about what we would want to do to apply Jowett's theorem. Suppose I've got some matroid which has got branch width bigger than W. I look at the corresponding connectivity system. It's going to have it's going to contain some small obstacle to, so some small thing where when I take the restriction to that set, the connectivity system still has branch width bigger than W, so say that's Z. But that's in the connectivity system. I have a matroid. My containment operation is minors. So I want to take an element out here and I'll try to delete it or contract it. But when I delete it or contract it, I may not get the same connectivity system when I restrict to Z. Right, I can open up new separations. But Chen and Whittle's theorem says that if the size of this matroid is much larger than Z, then I will be able to delete it or contract it, keeping the same connectivity system on Z. That's the content of the theorem. So it says that if you give me some set and I care about the connectivity system on that set, then I can remove all but a few elements, keeping that same connectivity system. Now, if you think, oh wow, that's nice, and you run away and you look at the paper, you'll say, that's not what they prove. They only prove a theorem about keeping 2 different connectivities. They don't. So basically, they look at keeping for 2 subsets of Z, they keep the connectivity. But if this is huge out here, when I delete the edge here, I might open up a separation that's bad for some partition of Z. When I contract it, I'll open up some separation that's bad for some other partition of Z. There's only so many partitions of Z. So if there's an enormous number of elements out here, there'll be a lot of elements out here that are bad for the same pair of partitions here. And Chen and Whittle say, no, 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 that can't happen. They bound, for a pair of partitions of Z, they bound the number of elements out here that can be bad for those two partitions, which is good enough. Okay? So this is great. So it says that if you give me a nice theorem on connectivity systems, I can use the result of Chen and Whittle to lift the theorem on connectivity systems back to a theorem on matroids that really talks about minors, not connectivity system containment. And it's any theorem. I mean, it doesn't have to, if you take a theorem which says your connectivity system contains an interesting restriction, I can take that theorem and I can turn it back into a theorem in matroids using this connectivity intertwining. So let me just give you a quick illustration of connectivity intertwining in this. So this is a vertex connectivity model. So I've got, say Z is the boundary of this grid. When I contract this edge here, I'm reducing the connectivity between the top and the bottom. When I delete the edge, I'm reducing the connectivity from left to right. And that's true for every edge. It's going to be, when you delete it or contract it, you're going to be losing connectivities between one of these two pairs. And what the theorem of Chen and Whittle tells you is that if you have a graph with this behavior, that I've got some set of vertices Z, and every edge has the property that when you delete it or contract it, you're reducing some connectivities in that set, then there can't be that many. Your graph has to be small. Right? That just bounds the size of the graph. If removing any edge reduces the connectivities between some partition of the vertices in Z, then the graph has to be small in comparison to the size of Z. So in this case here, the number of vertices in the graph is quadratic, is quadratically bounded by the size of Z. In Chen and Whittle's theorem, it's an exponential bound, but still, it's just exponential. And for all of the connectivity system models I've shown you, there are connectivity intertwining theorems. So I can go from connectivity systems to any one of them. The two cases involving minors both come directly from Chen and Whittle's theorem. Lee and Ohm basically use these techniques to get the result for vertex minors and pivot minors. And in the case of edge connectivity, this goes back to old results of Marder and Lovász. So you can take a vertex in a graph and you can do splitting off, keeping the connectivity system between the other vertices. You can reduce this vertex down to degree at most 3. That's what Lovász proved. So I can keep the connectivity system on the rest of the vertices and I can get the vertex down to degree at most 3. And if all of the vertices outside Z have degree at most 3, then basically edge disjoint path problems turn into vertex disjoint path problems, and you can finish things off with Chen and Whittle. There's a bit of hand waving there, but it's true. It takes a bit of work. Not much. So that says that if you take Susan's theorem, you can think about what branch width means in each of these cases. So in the case of this Boucher connectivity, you get rank width. In vertex connectivity, you end up with something that's very closely related to what's usually called branch width. So the branch width is sort of essentially the branch width. And in matroid connectivity, it is branch width. It is called branch width. And in edge connectivity, I think I've seen it called carving width. I don't know. So something like that. So you would get explicit bounds on the size of obstructions to those notions of widths under these kinds of containment by taking Susan's theorem and then just passing it through this machinery. Okay. So it would be nice if we could prove an analog of Susan's theorem for pathwidth. So I would really like to be able to say that if you give me a connectivity system that's containment minimum with pathwidth at least W, then I get some bound on its size. That would be great. I don't know how to do that. So then we ask, well, can we at least show that the number of obstructions is finite? And so if I can't bound the size explicitly, can I at least show there's only finitely many? Which usually means you're thinking about some kind of well-quasi-ordering type properties. Okay, so for those of you who aren't familiar with well-quasi-ordering, a quasi-order is essentially like a partial order. But with a partial order, you would be usually thinking of strict inequality. Things, you don't have, they're anti-reflexive, whereas quasi-orders are reflexive. You're less than or equal to yourself. So they're they're reflexive and transitive. That's what a quasi-order is. It's just something that's reflexive. It's a binary relation that's reflexive and transitive. And then you have two conditions to be a well-quasi-order. You have to have no infinite anti-chain, which means that if I give you an infinite set, then one of the elements should be less than or equal to another. And you shouldn't have an infinite descending chain, so you shouldn't be able to sort of repeatedly get smaller and smaller things in the order. So for example, the integers, which is a really nice quasi-order, it's a total order. The set of integers is not a well quasi-order because you do have infinite descending chains. However, in containment relations on combinatorial objects, like if I'm talking about minors, if I take a proper minor of a graph, I get a smaller graph, and so I can't do that infinitely often. So in combinatorial settings, we don't usually have to worry about infinite descending sequences. So for all the containment operations that we care about, we'll never get infinite descending sequences. So essentially, this well quasi-ordering means you don't have an infinite anti-chain. Right, effectively. That's what it's talking about. That's what we care about. And you would have all seen the famous theorem of Robertson and Seymour that the set of graphs is well quasi-ordered undertaking minors, which is a pretty spectacular theorem. I remember being really shocked when I was first told that theorem. Usually when you get told a theorem, if it's something that you sort of care about, you sort of could imagine a first step that you would think about trying before to try to prove it. This wasn't one of those cases. I just thought, how on earth would you prove that? And for those of you who aren't used to thinking about well quasi-ordering, let me just show you a couple of equivalent statements of that theorem just to sort of convince you that well quasi-ordering is a really nice thing to have. So this is the usual statement of the graph minors theorem that I just showed you. The set of graphs are well quasi-ordered undertaking minors. That's equivalent to saying that if you give me any minor closed class, it's described by a finite list of excluded minors. So the excluded minors for a class of graphs are an anti-chain. No one excluded minor is a minor of another, because these are the excluded minors, the minor minimal things not in the class. So no one is contained in another. And conversely, any anti-chain is the set of excluded minors for some class of graphs. right? So you just take all the graphs that don't contain any of those. So they're clearly just the same theorem. And so if I take a class of graphs that's got finitely many excluded minors, there's only countably many graphs, so there's only finitely many finite sequences of graphs. So countably many finite sequences of graphs, so there's only countably many different classes of excluded minors. Whereas if it wasn't well quasi-ordered, there'd be some class with an infinite set of excluded minors, and then every subset of that infinite set would describe a minor closed class. So I'd get uncountably many. So those three are equivalent. If I want to test membership of a minor closed class, I just have to, so I've got my favorite minor closed class and this graph, and I want to know whether it belongs to that class. This class is described by a finite list of minors, so I just generate all the minors of this and just see if they contain one of those. I'm not saying I can do it efficiently, I'm just saying I can do it. And so it clearly, I can decide, I mean, if I know there's only finitely many excluded minors, I can decide membership trivially. And since there's only countably many algorithms, this certainly implies that. So this implies that, so we're done. Those three we showed were the same, and then this implied that, and that implied that. These are very different looking statements. Like you've got, like, this is about certifying that something doesn't belong to a class. This is an algorithm. This is algorithmic implications. It's related to enumeration of classes and such. They're very different looking properties, but they all say the same thing. So it's nice. Like, minor closed classes are nice, and also pretty rare in some ways. So in terms of the things I've been telling you about, I just explained to you that this is well quasi-ordered. Amazingly, when Robertson and Seymour proved that this was well quasi-ordered, they had a really general model on hypergraphs that they proved a well quasi-ordering result for, and it simultaneously proved that immersion was well quasi-ordered. I find that amazing. So they actually have one theorem that subsumes both of these. For vertex minors and pivot minors, these are probably well quasi-ordered. There are theorems of Sung and Lom prove that in bounded rank width they're well quasi-ordered, or branch width, if you like. So from the point of view of the results we care about today, the Ohm's theorem at least says that for the things we care about, they are well quasi-ordered. Matroids are terribly not well quasi-ordered. Even rank 3 matroids aren't well quasi-ordered. I mean, they're a disaster. Connectivity systems are worse than matroids. They're a complete and utter disaster. Not even for bounded pathwidth. There's basically no interesting conditions you can put to make connectivity systems behave. I mean, they're just like under containment, it's a disaster. Same with matroids. Okay, so this is bad because I want to use well quasi-ordering techniques to prove something like Jowett's theorem for pathwidth, and this is not going to do it for me. So I need to come up with a different containment operation that might be a well quasi-order and which will still be useful for me. Will say something about the things that I care about, in particular, say something about pathwidth. So the first, I'm going to define what domination means. This isn't the definition of domination. This is the first step in defining domination. So if I have two connectivity systems, I'm going to say that K2 is bigger than K1 if they have the same ground set, and for every subset of the ground set, the connectivity in K2 is at least the connectivity in K1. I'll say that K2 is bigger than K1. And if I had K2 bigger than K1, then for any reasonable width notion I ever thought about, the width of K2 would be at least the width of K1. So certainly for path width, which is the one I care about. But width is telling me that I can break things apart across low order separation. So if all of the connectivities in K2 are bigger than the ones in K1, and clearly the width is just going to go up. Pretty sensible notion of width. But I don't want, it would be it won't be very helpful to have a containment thing which is basically just looking at sets on the same ground set. That's not useful to me. So I need to combine this together with containment. So we get a similar observation that if the ground set of K1 is contained in the ground set of K2, and the restriction of K2 to that ground set gives me a connectivity system that's bigger than K1, then it'd still be true that for any reasonable notion of width you ever wrote down, you'll have that the width of K2 is at least the width of K1. Right? So I've now just combined containment with big in the obvious way. And it's still not quite enough because we also, if we want to do some well-quasi-ordering, we're going to want to get rid of isomorphism, right? It's like when I say that a graph, in the graph minus theorem, I really want G1 to be isomorphic to a minor of G2. If they've got different ground sets, I can easily make infinitely many graphs where no one is a minor of another by just putting them on different ground sets. So there's always something where you have to have isomorphism. So if you combine big, isomorphism, and containment, you get the obvious thing in its domination. So we say that K2 dominates K1 if I can restrict K2 to some set to get a connectivity system. And then I can take an isomorphic copy of that, and that thing that I get is bigger than K1. That probably isn't what I wrote, but that's right. If you take K2, you restrict it to a set, take an isomorphic copy. If that copy is bigger than K1, then I'm going to say that K2 dominates K1. And again, I've just put these things together, so under any reasonable notion of width, K2 is going to have width, at least the width of K1, if this happens. And our conjecture is that unitary connectivity systems are well quasi-ordered by domination, which would be nice. That would really say that, in some sense, connectivity does behave well. It would be a surprising theorem. And what we were able to prove is that this is at least true if you restrict yourself to connectivity systems of small path width. And that implies that that you get finitely many obstructions under containment to path width. And this seems a bit weird though, right? So what this really tells you is that you get finitely many obstructions under this domination property. So the only thing we introduced to go between containment and domination is this notion of bigness. And so for any given connectivity system, there's only some constant number of there's a constant number of other connectivity systems on the same ground set, and I'm only interested in the ones that are bigger than it. So I just need to take the obstructions in the domination case and replace each of those connectivity systems with connectivity systems on the same ground set that are bigger than it. So that's only going to give me finitely many obstructions. So even though this was to do with domination, you still get a result on connectivity systems. Containment in connectivity systems. This is somewhat similar to, if you give me a minor closed class, so if you take topological minor closed classes, they can have infinitely many excluded minors. But if I take a minor closed class, you get finitely many excluded minors, and then you can turn those into a finite list of forbidden topological minors. So every minor closed class is actually described by a finite list of excluded topological minors, whereas arbitrary topological minor closed classes can have infinitely many. This is the same kind of thing. Within domination closed classes, you get finitely many obstructions under restriction. And the final thing I want to mention is that those two theorems seem quite far apart, and I don't just mean in terms of typesetting. And, but in fact, they're not so far apart. And the way you see this is by thinking about what the natural, this is a word, I like this word. I learned this word from Neil Robertson. He calls things omnivores. So for example, complete graphs are omnivores for graphs under subgraphs. Every graph is a subgraph of some complete graph, so the complete graphs eventually eat all the graphs. Grids are omnivores for the class of planar graphs under minors. Every planar graph is a minor of a grid, so the grids eventually eat all of the planar graphs. So what are omnivores for unitary connectivity systems? So I take a connectivity system on ground set 1 up to n, but if I take a set A, its connectivity has to be at most the size of A, because of the unitary property. And it also has to be symmetric, so it has to be, also the connectivity of A has to be at most the size of its complement. And you can put a quality here, and you actually get a connectivity system. And this is, in fact, the connectivity system you get by taking that vertex connectivity model I gave on a complete graph. So the connectivity system dn dominates all unitary connectivity systems with n or fewer elements. Right, so these are omnivores. And it turns out that if you give me a unitary connectivity system with branch with at least 3n, then your connectivity system dominates dn. This is not a difficult theorem. This is a standard theorem in tangles. This is basically related to highly connected sets. So for those of you who have done tangles and heard highly connected sets, you probably sort of half see where this comes from. And this means that if you look at an anti-chain under domination, so you certainly can't contain arbitrarily large omnivores, because they'll eat up the other elements in the anti-chain. But that also means you can't have arbitrarily large branch width, because large branch width gives you large omnivores, and that'll eat up the other elements in the anti-chain. So that means that, that if you want to prove this theorem, it's enough to prove it for unitary connectivity systems with bounded branch width. And that doesn't seem so far from what we proved. We proved this for bounded path width, and we need to prove it for bounded branch width, which doesn't seem like such a big stretch. Okay, I'll stop there. Thank you.
Questions? Have you thought about what happens when the ground set's infinite?
Never.
But it's not going to have all the d-spilly pathologies to do with infinite graphs, because you somehow, if all the connectivities are integers, then it's kind of like you don't have analogues of infinitely large vertex separations, which are what make infinite graph connectivity really difficult. And pathwidth is also straightforward to define. So I'm wondering, presumably you're reducting on the size of the ground set at some point, but I'm wondering how fundamentally your techniques would break.
I'm always scared to think about infinite objects. I think it probably, I mean, it doesn't sound like it wouldn't work. It just is not something I've thought about at all. I think the man you want to talk to is Rutger. He would love that question.
Suppose the ground set is m vectors of length n. Okay, so in other words, an m by n real matrix. Let's say that's your ground set. What are the natural? Are there any natural connectivity systems? Are there many for that ground set?
So am I looking at vectors or matrices? You're saying
Vectors, yeah. In other words, the whole thing is a matrix. If I put all.
okay. So that's a matroid.
Okay.
So the connectivity system is the connectivity system for matroids. It's actually a matroid in two different ways. But maybe it depends. I mean, it depends on very much how you're coming to that system, because very often when people think about a matrix, they will be really, I mean, either you've got a very different sense of the rows and columns as to how they come up, and if there's like really like you care really about these things as vectors, not as a matrix, then probably you really are thinking about the column matroid, and then you are asking for the rank of A plus the rank of B minus the rank of the matrix as being your connectivity. That would be because the subspace spanned by that plus the subspace spanned by that minus the rank of the whole thing is like the common span of these two things. Like that's Tutt's thing. But if you come about matrices in other ways, then often you're thinking about really there being a leading identity. I mean, it depends on how you get to it, right? So sometimes people are really thinking about a matrix where there's some sort of hidden identity, and then you would be looking at something like the sum of the ranks of these two parts. So depending on what you care about in the matrices, you'll end up with different answers.
That's the entanglement in graph states. So is entanglement in quantum states a connectivity system, not restricting to graph states?
Ooh. If I wanted to know the answer to that question, I would ask you. So is that I don't know.
In the end conjectural theorem, is there a simple reason why you look only at unitary connectivity system?
So why do we only look at unitary connectivity systems? Because life gets really complicated. It's not at all.
So you don't know if it's false?
I don't know if it's false. I don't even know if I would. I don't even know which way I'd guess. Like if you replace unitary if you put a bound of 2, I really just generally don't know whether it should just all fall apart or not. It's surprising. It's surprisingly non-obvious, even in the Pathwidth case, what you should do. Yeah, I'm not going to say any more. I don't know.
Any other questions? All right, let's thank Jim again.